All right, so thank you everybody for taking the time to join this webinar. My name is Phil Glennie, the Director of Sales and Marketing at Long-Term Technology Services. We have a slide about our company to introduce ourselves to you a little bit later on. But today, let's just focus first on the presenters today. So we'll be leading with myself, followed by my colleague Tungwon, who is the Director of R&D and Commercialization at Long-Term Tech, my colleague Pan, who is a Research and Development Engineer here at Long-Term Technology Services. And we're very happy today to be joined by Mark Lamping, a Mechanical Applications Specialist with Siemens Digital Industries Software. Now, to avoid sucking up too much of the bandwidth throughout this presentation, I am going to close my camera right now and let you all focus on what is important, which is the presentation. Okay, a little bit about today's agenda. I'm going to start with a high-level introduction to the subject matter. Then we're going to get into today's subject, which is simulation for designers. Basically, this concept of shifting simulation activities more into the design stage of engineering and the benefits that can be had from doing that. From there, I will turn it over to my colleague with Siemens, Mark Lamping, to talk about some real-world applications and to demo some FEA capabilities. After that, we will turn it over to my colleague Pan to talk about some fluid flow analysis, and then we will have Q&A and a prize giveaway at the end. So if you want to ask questions throughout the presentation, please feel free to type your question into the chat box. We will make sure to answer them throughout the webinar and during the Q&A at the end. Now, a little bit about us, if you don't already know us. So at Long-Term Technology Services, we are your trusted digital industry partner. We are very deeply experienced in simulation for product design and engineering. We cover everything from CAD, CAM, CAE, virtual commissioning, process design, simulation, plant simulation, all kinds of things that we'd be happy to talk to you about. We're the trusted partner of many, many companies in Canada and the US, specialists in helping companies reap the full rewards of digital industry software, and we are a proud Siemens Smart Partner and Technology Partner. Smart Partner means that we are certified experts on Siemens software. Technology Partner means that we have a team of developers who perform their own software development on top of the Siemens software. That's another added benefit for our customers and partners who might need some more custom stuff built. So a little bit about the trends impacting what we're talking about here today. So the current challenges and opportunities for CAE. To start off, manufacturers across the world are facing many of the same challenges. So CAE for many is a bottleneck in their product development process. They need to really drive down their product development costs. They need to decrease their time to market, which is more and more important in a world of very long lead times. They need to be more innovative, and they have to have better performing products out there. And they need to reduce their operational risk and compliance. And all of these things can be satisfied by better use of simulation. This slide really shows, this tip of the iceberg type of metaphor you have here for the later that you catch a problem defect in the product development and engineering lifecycle, the more expensive it is going to be to address that defect. Think about finding something out at the physical prototyping stage, right, versus the early CAD concept design. People who are using simulation nowadays really need to answer these types of questions, right? Very straightforward things. Will it break? Does it get too hot? How long is it going to last? Is the motor the right size for the load that you're using? Can you make it lighter? How efficient is your cooling? Now, for a lot of companies, simulation can really feel out of reach, and the reason for that, right, is that simulation is often associated with CAE experts, right, often PhD level people in simulation who work on very complex softwares and models, and you add that all up, right, and that costs time and that costs money. And what that does is it creates a bottleneck in the overall product design and engineering workflow. Because what you do is you get design one, you bring that through to the first simulation, bottleneck, then you get into the next iteration, another bottleneck, and you really need to wait on these people who are doing these designs. And then you don't really know when you're going to get to a release because you keep redoing it, sending it back, redoing it, sending it back. So what is the solution to doing it this way? The solution is simulation-driven design. And what that really means in the context of what we're talking about here is shifting more simulation activities into the hands of your designers. Now, you might have some immediate questions that come up with doing something like that, such as, how do we ensure that this is going to go the way we want it to go? Designers don't necessarily have expertise in simulation methods and techniques, and simulation, quite frankly, requires many years of experience and education to know what is right and wrong. How can we trust this workflow if we're putting this in the hands of designers who haven't been trained on this and basically have not been asked to do this previously? And the way that you do that is that you lower the training barrier by making the simulation process more accessible to your designers. And you also get a much tighter collaboration between your designers and your, trained analysts, and allowing those analysts to guide the designers or those infrequent users on simulation technology. Now, those are the human ways that you can address the issue. But what about the technological ways that you can address this issue? So first, we are recommending out-of-the-box CAD integrated simulation. So what we're talking about here is simulation tools that are built directly on top of the CAD modeling environment, right? So you get the associativity between the simulation model and the CAD model, and all of the efficiencies that come with having those two models synchronized as you design, iterate, simulate. And you do that very, very rapidly compared to the previous process of doing a lot of design, simulate, a lot more design, simulate. The second thing you can do is you can automate routine simulations. Even if these are advanced simulations, there are ways to automate those. You can use templating, for example, in your simulation tools, and you can use that to really put guardrails on what your designers are doing with simulation. And that is something that can really be overseen by a CAE expert, designing those templates and really automating a lot of those commonly used simulations. So when you do that, you take the old way of doing things and you do what's called shifting left. And what you're doing here, now you're getting much more iterative here, right? You're rapidly designing and simulating in quick succession to compress this overall timeline. And that has a lot of benefits. That's not just going to reduce your lead time, right? That's going to completely change the way that simulation impacts your overall workflow. Because if you're using simulation, very rapid simulations in the early concept stage, you're going to discover a lot of new design possibilities. And, especially if you have rock solid confidence in the accuracy of those simulations, you're going to iterate, innovate, and improve on your designs much more rapidly in those early concept phases. From there, you get into the design stage, and you're going to increase your overall design robustness while speeding up the development process. And then finally, when you get into this traditional segment, right, this traditional phase of validation, this is going to go much faster because of all this upfront work you've done within the design phase. So you're going to rapidly validate to meet those performance requirements. Now, the next thing people often ask when we talk about shifting all of this left is, okay, well, you shift this left and you put it in the hands of the designers, but what about the complex simulations that truly do need those, those very high-end solvers, right? Those very high-end complex simulation engines and products. So what we're talking about here is scalability. So as the user's experience gets larger and the problem complexity gets larger, what you can do is you can start designers out with single part analysis. You can scale that up to assembly level analysis. And then, right, as you get more experienced users like CAE experts, you're really leaving to them, right, those high-end multi-physics, the assembly level stuff that really, really requires that expertise. And you're shifting some of the more routine types of simulations into the hands of the designers that will then be quality checked by the CAE experts. And there's a very clear upgradable path here, right? So the product we're going to talk about today, Simcenter, it gives you everything from, your single part analysis through to any world-class simulation solver you can imagine that is accessible through this. There's really no level of simulation you can't get to with it, depending on how much you need to scale. A study by Aberdeen Group has really outlined well the benefits of choosing this approach, simulation-driven design. So 73% of best-in-class organizations use simulation during their detailed design phase, and on average, a reduction of roughly 30%, right, in development time for best-in-class designers who are using simulation-driven design. So now that we've talked a little bit about the concept of simulation-driven design and shifting left, we're going to talk a little bit about the solution that we feel is best suited to actually realize the promise of that kind of activity. And we're going to talk about Simcenter 3D. So Simcenter 3D will cover, anything from topology optimization to structural simulation, your thermal flow, your motion, your vibration. And then you can even get into the more advanced physics and capabilities where you're getting into like durability, acoustics, electromagnetics, additive manufacturing simulation, multi-physics, design space exploration, all this more advanced stuff. You can do any of it. Now, typically with 3D simulation today, you have a lot of really disconnected and ad hoc processes, right? There's no common model being used between your CAD design, structural analysis, thermal analysis. You're kicking it over here, but there's no common model at the heart of all that. The great thing with Simcenter 3D, because it is built on top of the CAD modeling environment and all of these modules are embedded and can be added to the main platform, then what you do, what you get is you have a common model at the heart of all of these activities, right? And an associative connection. So if somebody does something in simulation, that is reflected in CAD, right? And when the CAD is updated, that can very rapidly be kicked over to structural analysis, simulate design, iterate on the design, simulate again, iterate on the design, simulate again. From there, you really begin getting that faster initial iteration on this traditional process of, importing, editing the geometry, doing your meshes, your loads, boundary conditions. You're compressing all of that because of that tight associativity between the CAD and the CAE, having it in a single platform. And then you can rapidly update on that for later iterations, right, as you design, simulate. Now, today's demonstrations are going to be broken into two products, right? So Simcenter 3D, which we're going to show you for the FEA structural, and then Simcenter FloEFD, which we are going to show you for the fluid flow analysis. Now, before I send it over to my Siemens colleague, Mark, I'm just going to go through some quick case studies here. So a company many of you might be familiar with was asking, how can front-loading simulation in our design stage help us reduce cost? And I kid you not, Renault used Simcenter to reduce the cost of their headlamps by 50% in 2 years. And they were doing that mostly by using thermal simulation within their design process to reduce the package size of their headlamp while still maintaining the thermal performance of that system. Next, we look at a company like Guangxi Yuchai Machinery, which is the largest producer of internal combustion engines in China. They use simulation-driven design to help them meet market demands for more personalized products. Now, this slide is more about how does it help you get to market faster? So as a company has greater personalization in their products, that means more product categories, right? But this company had very limited dedicated CAE resources. So it became impossible for them to feed the analysis results back to the design engineers. So basically, they just put the design tools in the hands the simulation tools in the hands of the designers. And they started using simulation to get really immediate feedback on how their designs would perform. Next, a company might ask, how does front-loading simulation help me reduce overall risk? In this case, Design Automation Associates, they automated their simulation processes used to analyze the performance of their, these are engineered to order products. So their routine simulations might be performed up to 100 times or more per year for every variant. And that means errors can become very costly and time-consuming across that many simulations. So by automating those processes and having their designers perform the simulations, they were able to reduce errors and they were able to achieve a 100 times faster process, according to their own internal team. How does front-loading simulation help me be more innovative? Mitsubishi Materials Corporation used simulation-driven design to study various variants to optimize the liquid cooling channel opening. That's like the geometry of the cooling channel opening to improve their cooling system performance for advanced cutting tools. So they actually didn't have any specialist CFD analysts, but their designers were able to perform the basic analysis easily inside their CAD environment, and they were able to achieve an 11% increase in flow rate through the cooling system. And then finally, a company that many of you know probably well and will factor into your lives if you're traveling this summer, Samsonite also uses 3D simulation to do their tests right on their bags. This is a company that traditionally would use a lot of drop tests, a lot of tumble tests, right? Really beat up these suitcases. That process, that manual process, physical process, is roughly about 16 weeks. they dropped that down to 1 week by pulling all of that testing into the Simcenter environment and having their designers work on that. So that's just a quick look at basically we've gone over the trends in CAE, this concept of shifting left to simulation-driven design and where that's coming from, why that's happening with these companies, and then the suitability of Simcenter to really fulfill that because it is built directly on top of the CAD modeling environment. So with that, I am now going to hand things over to my colleague at Siemens, Mark Lamping, to take us through the next section of this presentation. Mark?
Yeah, thank you, Phil. And I will share my desktop and go into slideshow mode. And so I'm going to start off with a case study from Denso. Denso is a automotive OEM, or they're an automotive supplier, and they are looking to ways to improve their design quality, um, provide designs on time, and use more simulation in the context of design. And this is taken from a presentation that they gave at a users conference. Move this out of the way as well. Okay, so then on the first slide, we're talking about their previous situation where their designers and their CAE specialists are, kind of siloed. Their designers are working on only design tasks. They're not doing a whole lot of simulation. They're doing some, but not nearly the amount that they need to do. And they're relying on CAE specialists to do more detailed simulations. And so you see here a discontinuity in the tools that are being used. The designers were using NX. The CAE specialists have their own set of tools that they're using. There's communication that has to occur. There's requests. They have to request the CAE specialist to do the job. And on the next slide, we see the current problems in that environment. And from the designer's point of view and from the CAE specialist point of view. From the designer's point of view, we see long lead times. They ask for CAE analysis to be performed. It has to get scheduled, and then a couple days down the way or weeks, they end up with some feedback from the CAE specialists. And it could be to a point where they're getting that feedback too late. They've already released their design for drawings, and then a problem may be identified too late, and then you're into a situation where engineering changes are needed. Designers' thought process and activities may be interrupted because the information isn't coming in a timely fashion. From the CAE specialist point of view, they have a large workload already, and they have a decreasing motivation to perform these designer-oriented tasks. They want to focus more on CAE technology development, maybe some nonlinear and product kind of multi-physics type of analyses. But the work still has to be done, and the work requires time and effort. So let's try to figure out how we can do the work and reduce the time and effort. Yeah, the designers and the CAE specialists could have communication barriers, and the wrong information may be leading the CAE users down the wrong path, but they may do the analysis anyway and find out too late that they started down a wrong path, and then they'll have to start over. So neither the designer or the CAE specialists are really too happy with this setup. The solution at Denso was to provide a simulation environment for the designers using Simcenter 3D and its tight integration with the NX CAD environment. This is combining CAE templates and a bit of automation around the CAD and CAE tools. Um, this was really ideal for them because it is based on the NXCAD platform, which is their designer's familiar tool. And we see on the final slide um, some summary points. So by enabling the designers to run standardized CAE work, the CAE lead times were shortened drastically. This NX simulator environment uh, enables the designers to get high-level results much more efficiently. They're using CAD model attributes as part of the CAE templating process to build these CAE models, and it is streamlined their model build pre-processing work significantly. The reuse of those attributes and the fact that 80% of the Denso work is involving that iterative process. They're just repeating work over and over. And even if they go from a different product line to another, it's a similar product, so they can use the same CAE templates. Um, and this repeated work and the use of templates in those environments um, reduce time to analysis results as well. The designers, they improve their design skills by running CAE, and just the fact that they're doing that makes them better designers, and they can, get to a better solution faster, all by themselves. There is a Denso case study in this presentation, and this link will take you to a case study article written in conjunction with Denso and Siemens. And it describes their use of the Simcenter 3D environment to streamline their design workflows. So I encourage you to take a look at this, and um, hope that maybe Phil or one of the others could drop this link into the chat right now. Then we go on to the templating topic. So what are Simcenter 3D templates, and how do they help build your FE models starting from CAD data? So yeah, step one, we have CAD data and we want to run an analysis on it. So step two would be the creation of a FEM file in Simcenter 3D. This is where we would generate meshes, assign material properties and physical properties and so on. And a CAE template is used when you create a new FEM, and those templates can contain things like materials, physical properties, different types of meshes from 0D to 3D, mesh controls, and so on. And so they think of these as like overhead items that a user is going to have to apply anyway. And if you can jumpstart the process of building a model with content already in it, the process will be much faster. And this third step here is defining a SIM file, which contains solution setups, loads and boundary conditions, and certain aspects of recovering outputs. So all of this is stuff that would be supported in the template as an object that exists and then is easily populated with geometry through selection recipe capabilities. So selection of geometry by attributes. And that takes us into the benefits. We reduce our repetition. And when by using templates, we take a lot of tasks that we do over and over, and they capture that in the templates. We enable consistency across the enterprise, so we can deploy these templates to the entire enterprise, and any number of users could be using the same templates. You're always going to get consistent output across those sets of users because we're using a guided approach to these analyses, and then we're accelerating decision making as well. And I'm going to show 3 videos here to describe the templating process. The first one is a review of a template. So I'm going to open up within Simcenter 3D a template. It's just in this case, it's going to be a FEM file and then a SIM file. If any file, any CAE model can become a template. And uh, there's no geometry associated with this model yet, but it has meshes. You can see 3D meshes there. And those meshes have selection recipes associated with them. So there's one recipe that picks up a solid body and it's colored red. Another picks faces with certain names. So there you see a list of 3 names, 4 names there. And if we go into that mesh, we edit it. It has an element size and certain properties, and it has a selection to a recipe, which is an attribute-based selection. It's not actually picking the geometry, but it's picking an attribute that is assigned to the geometry. Now we're going to go open up the simulation template, and we'll see that it already has a set of solutions defined. It's got loads and boundary conditions already defined, and the assignment of all of these are based on attribute again. When we go to the next video, we're going to show the actual creation of a FEM from geometry and the use of one of those templates. So that same template that we just reviewed. So we have our CAD geometry, and we may want to first assign attributes to this geometry so that it can be used in the template. And our attribute today is color. So we're going to color this solid body red, and then when we mesh it, we have a mesh that will mesh the red bodies in a certain way. Similarly, we assign this color of that pin to be black, and that is assigned to a mesh that it'll mesh only the black solid bodies. We have face names that we can assign. So on this face, we call it bearing 1, and that's going to be associated to a load in the simulation. Here's an example of, I maybe pause this temporarily. Well, I'm just going to let it go. But it's showing an NX Open application where it's got names pre-populated for those. So that NX Open application is taking away user error in terms of input and assigning these attributes. I did a visual report of our faces by name to ensure that I've accurately named the faces for my simulation. All of this, right, is being done in the CAD model in preparation for use of the template. And then I finally get into generating a new FEM file, and I see a listing of different templates. I've got my custom template, my customer-specific template that I select there that I showed it previously. And what we're going to see next is it's going to start generating mesh content without any user interaction. It's just I created a new FEM from that template, and I'm already getting meshes based on the properties of the CAD data. And there is one body that's not meshed yet. You see an element count of 0 on that 20 millimeter mesh. And there's a selection recipe that it doesn't find anything. If we look at that, it's going to look for bodies that are blue. So we want to change the color of that body to be blue, and we immediately see an update for our CAE model. We update the model, and now that last component is meshed a particular element size. The materials are already assigned. Those materials were inherited from the CAD data, the material assignments on the CAD side. And we also see a face density. In a local area, I have a local mesh size throughout a number of the faces in the model. And then the last step is to create a SIM file from from the template, starting from the previous video. We're going to create a new simulation, and our custom template has a linear statics and normal modes solutions in the template. It's got a bunch of loads defined for that linear static solution. It's got frequency ranges and constraints for the modal solution. You see the loads and the constraints are already populated with content. They've got faces selected for those bearing loads, a face selected for that fixed constraint, and that's due to the use of attributes to find those faces in the context of a constraint or a load. I also have a result probe defined, so this is a way to calculate user-defined type of results. So I can customize the kind of output that I get that's captured in the template. If I look at the normal mode solution, I can see that it's got its own specific frequency range or the number of modes that it wants to calculate. And so this is a template that's going to be generated by the CAE expert, but handed off to the designer for use. So it's a guided approach to the simulation process. And sorry, I need to get to my slider here for the time. This is showing the solution, and then once it solves, it's done solving both of those. We can post-process either interactively or using things like snapshots and reports to get a view of more of the templated output from this overall CAE template process. So that's the content that I wanted to show. Phil, I guess I can stop sharing at this point and hand it back to you.
Mark, thanks so much. Yeah, that was a fantastic presentation, and thank you for everybody for using the chat box here to ask any questions you're looking to ask. As we continue on, we will have also a dedicated verbal Q&A at the end, but I will now pass it over to my colleagues Pan and Tung Nguyen to talk about fluid flow analysis.
Thanks, Phil. So in this presentation, we will use an IGBT liquid cooled module as an example to show the workflow of running CFD analysis from start to finish using Simcenter FloEFD. So FloEFD is a front-loading CFD tool for designers. So the designers, it has been especially developed for non-CFD specialists to get fast and accurate results. So it supports multiple versions, such as the standalone version and the CAD embedded version for NX, Creo, SolidWorks, and other CFD tools. So the first step, I just want to examine the IGBT component. So if we use explode function to explode the assembly, we can see the parts that make up the IGBT module. So we can see the casing, the silicons, and the heatsink copper. So there is additions of the leads, which serve the purpose of closing the water region and for applying the flow boundary conditions. So next, let's take a look at the cross-section. So we can see there is some geometric overlaps between the part at the O-rings and the silicon potting compound. So FloEFD has no issues with overlapping and dirty geometry. So there's no need to spend time fixing this, but you need to be careful with the material priorities. And we can activate FloEFD from files or application simulation and FloEFD simulation. So we can see the addition of the flow analysis tab showing, and which is used to control the analysis. So finally, let's use the FloEFD check geometry functionality to check the fluid region. And the fluid region are shown on the screen highlighted in blue. So there are some small enclosed volumes around the O-rings. This will be ignored later, but the main fluid region has been detected correctly. So this fluid part doesn't need to be created in NX. It's automatically created and updated. So now the geometry is ready for FloEFD analysis. The FloEFD analysis setup is wizard-driven. The first step is just to name the project, and then you need to pick the unit system, which can be customized if needed. And this project is an internal analysis, and exclude cavity without flow condition is enabled to ignore the previously seen cavities. And the heat conduction in solids is enabled to consider heat conduction and convection. And water is chosen as the working fluid. And for the solid part, the aluminum is chosen as the default solid material. The wall conditions are left to be adiabatic to ensure all the heat is transferred to the water. And the ambient temperature is set to 65 degrees C to replicate the under the hood working condition. Once the wizard is finished, we can see the computational domain around the assembly. So next, we are going to assign material properties. So we are applying silicons on the chips themselves from predefined FloEFD material library. So since FloEFD is CAD embedded, we can just use the assembly navigator and go to the structure tree and just click the component there. So likewise, we can assign corresponding materials to each solid part. So next, I'll show you how to add flow boundary conditions. So here, I want to use a constant volume flow rate at my inlet. We can just insert a boundary condition and hide the casing for easy application. And later, we will just select the interface of the inlet lead and apply the value. And similarly, we can apply a pressure boundary condition at the outlet lead. Last, I want to show you how to add a heat source. Here, I want to add a heat source through a volume source to these chips. So again, we are going to use the structure tree to select the corresponding component. For example, here I want to add a heat source with 360 watts on the IGBT components. So the power will be split across the selected bodies. Likewise, we can apply a different heat source onto diode component. And in Simcenter FloEFD, we use goals to monitor if the simulation is complete. There are many ways to add goals. And for now, in this model, we have surface goals at the inlet and the outlet to monitor the pressure, temperature, and the volume flow rate. And we have the volume flow goals at the IGBT and the diode component to monitor temperature, and I have equation goals to monitor the pressure and temperature variation between the inlet and the outlet. And in terms of meshing, currently I'm using the automatic mesher with level set to 4. So all the subdivision is based on the current mesh level. But you can also use a manual mesher as needed. Here you have more control over the meshing. You can determine the number of cells, or you can also adjust the mesh based on the curvature level and the curvature criterion. You can also add a local mesh refinement to the component. For example, you can add local mesh refinement to the heatsink component. Once everything is set up, you can just hit run to solve the model. As you can see, the mesher has to be run before the actual solver, and both mesher and solver are parallel compute enabled. You can utilize as many cores as needed. So the model has been run and solved. So next, let's just load the results to see the generated mesh and the ways of showing results. So same as the pre-processing, the post-processing is using the same environment. So first, let's take a look at the generated mesh on a CAD plane. So it shows the mesh level from 0 to 2, and 0 shows the base mesh, and you can see the mesh refinement occurs along where the liquid and solid interaction occurs. And notably, the mesh refinement cannot skip a level. It can only goes from 0 to 1, 1 to 2. You cannot have a level from 3 to 1. So it's very important for solver robustness and the convergence behavior. Next, I would like to show the ways of presenting results to your team and across your organization. So first, let's take a look at like the temperature results at a CAD plane. So here it shows the fluid temperature, and you can also show other parameters. For example, the pressure, if you are interested in the pressure drop during the simulation, and then you can also show the fluid velocity. You can also show temperature results on a surface. So next, I'm going to show temperature results on the heat sink. So here you can see the temperature variation on the heat sink. You can see the hot zones next to the heat source and the cold zones where it's in contact with the moving fluid. You can also use the probe to identify the temperature results. And the flow trajectory can be used to show how the flow moves through the fluid region. And the flow can be animated and exported if desired. So animating the flow is used for detecting the recirculation zones and the area with high velocity speed. So next, I want to show you the ways to show some quantitative results. For example, NX sketches can be created and used for results extraction. Here, I have created a line along the bottom of the heat sink, as you can see from the graphic window. So here we can plot the pressure and the temperature changes along the path. Later, the data can be exported to Excel for further processing. And a report can also be created based on the templates, which can be customized to export only selected data if required. So last, I just want to say you can also export the results to Simcenter Nastran for structure analysis or for fluid structure interaction simulation. Yeah, I feel this is what I want to show.
Fantastic.
Yeah.
Yeah, well, thank you very much, Pen. So that brings us basically to the close of the demo section of today's presentation. So Thank you, everybody. So I'm now going to switch the screen back to mine for the Q&A portion. I do see some Q&A activities that have been occurring over in the chat, but does anybody have any questions they would want to ask to the group now? And while everybody is thinking about them, I actually did have a quick one for Mark. So Mark, when we were talking about the benefits of the CAD embedded simulation, right? The fact that that Simcenter is embedded within the NX CAD environment. So how does that apply to companies that are not using NX for their design?
Yeah, that's a good question, Phil. And we do have examples of that where a company is using a third-party CAD, but then sending CAD data to Simcenter 3D through different translators, and from an update point of view and a AE model update point of view, probably the best one to have is JT. We can update a CAE model from a JTCAD input just by taking updates to the JT.
Right.
So the third-party CAD design, it evolves and it generates a JT that we can start using for our CAE work. You can apply one of these CAE templates to that geometry. And then as the design progresses, it goes to milestone number 2, 3, 4, 5, just generate another JT and use that JT either on the same model, which we can then update our geometry from that updated geometry, or run your templates again on the new version of the geometry. That's always an option as well.
Right. Sounds good. I see we have a hand raised. Paul?
Yeah, I kind of a two-part question, I guess. I'm assuming this would be compatible with Mold Wizard in NX, and then there was some discussion about different attributes. What kind of attributes? You talked about materials and so on. Are these like drop-down menu type pull-downs where you can grab materials, or you have to get the materials and input all the information? How does that all work?
So I'll answer that. So the material assignment would be through the standard material capabilities inside of NX and Simcenter 3D. You have the ability to create materials. We have libraries of materials that you can generate, and then you can assign materials to bodies, solid bodies or sheet bodies. And on the CAE side, we can inherit those material assignments on body levels to our meshes. And then there was the other part of the question was about attributes. And inside of the CAD model in NX, you can assign attributes. There's an edit properties command, and in there you can define attributes on any piece of CAD, so a point, a curve, a face, an edge, a body, and depending on what the nature is of your need on the CAE model, if you need the face, well, you could define the attribute on the face. If you need a curve, you define the attribute on the curve. And by attribute, I mean like colors, names of objects, and then just user-defined attribute. I have an attribute that is CFD, and it has a value of inlet or outlet. That's kind of referring to when I talk about attributes. And those attributes can then be the basis for your selection of objects inside the CAE model. The selection for a mesh, a selection for a load, or a boundary condition.
Mark, I was also curious to know, when you see this sort of like approach, right, like simulation for designers being used in the real world. I mean, we talk about that rapid, redesign, simulate kind of iteration happening. What kind of range have you seen in real life, right, in terms of like the number simulations people are performing to get, product to the ideal design variant?
So just take it like, and instead of, the traditional approach that you showed is you're doing an analysis at maybe every other or every third milestone, and maybe a milestone is every 2 weeks in the design process. I mean, that's what the graphic is trying to show. And then the second piece is, well, now I'm able to do an analysis at every milestone. So every 2 weeks, I'm able to finish my analysis work, because I'm able to keep pace with the design milestones. But the reality is that, some of this is you're iterating within the milestones themselves. So a designer is able to iterate on, he's updating the design every 2 weeks, but during that 2-week period, he may have come up with 20 different design concepts that he tested out. So
Right.
that's kind of the speed up that we're looking at.
Yeah. Okay. Well, I want to thank everybody very much for coming. Thank you again to 3D Connection. Thank you very much for Mark for joining us from Siemens Digital Industries Software. Thank you for the knowledge that you shared. I hope everybody learned about this new trend in simulation and how it's going to be pulled more into the work of designers and how that's happening across all industries. And happy to follow up with any of you after the fact if you would like to know more. Thank you very much for coming and have a wonderful day.
Thank you. Really appreciate this today, Phil. Thank you for putting it together.
Thanks so much.
Yeah, thanks very much.
Thanks,
Thank you.
everybody.
Yeah,
Bye-bye.
bye-bye.
Thank you.